All right. Well, good morning, and thank you for attending today's webinar. This is going to be featuring hybrid heating solutions, and I've invited Tobias Schneider, Business Development Leader for Honeywell Thermal Solutions. Tobias has quite a bit of experience in the industry. He's been with Honeywell for almost 4 years, and his current position of Global Sustainability Business Development Leader for almost a year. Tobias will go through and share a little bit about what Honeywell has been doing in the hybrid heating space, showing what kind of solutions and applications that they've been working with now that they have solutions available for today's applications. Tobias is based in Germany, and he'll show examples of some of the projects that they have gone through and done in Germany and in Europe. But the idea is that we want to share what they're doing over in Europe to the customer base here in the United States, because I'm very excited about the direction that Honeywell's going with these hybrid heating solutions, and I'm happy to have Tobias with us today. So before I turn it over to Tobias, I just want to let all of you that are attending know that we will have time set aside at the end of Tobias's presentation for questions and answers for myself and for Tobias. So feel free to post your question and answers in the Q&A tab on the Zoom app. And if you do have, I will be monitoring those questions. If there is a natural time where I can interrupt Tobias to ask him the question, I will do so. Otherwise, I'm just going to let Tobias continue with the presentation and reserve those for the end. Some of you that are listening now may be listening to the recording of the webinar, and I will let you know that through the Training Center website, there will be a link or contact information so that you can reach out to me so that we can answer your questions after this recording is done. So without further ado, I'll turn it over to Tobias. So Tobias, take it away.
Thank you, AJ, for the introduction, and welcome everybody for today's presentation about our hybrid heating initiative. So to kick us off, I want to go a bit into why are we investing resources, money, and a lot of time and sweat and blood into a hybrid system. And here's the reason. The world is changing. We see changes in global temperatures, rising oceans, food crisis arising exactly out of this. There is a significant higher health risk. We're going to lose species down the road, sooner or later. Severe storms are hitting globally everywhere. We just last year had a thunderstorm in Spain where portions of Spain looked like afterwards to belong to the ocean. It was completely gone, not seen before. Increased in droughts. Look west in the US, look to California and the West Coast. You see significant drought now going on for years. It's not getting better. And this changed the perception globally. Our industries are working on reducing carbon. And if you take a look at how much the industry is emitting, it's about 30-ish% of carbon dioxide coming from industrial applications. The other parts is housing as well as transportation. With this, the majority of the global countries are investing a significant amount of money in becoming cleaner in terms of energy. China, US, also Germany, we are spending significant amounts of money to support this transition in energy. But now comes the most important point. What scenario will win in the future? If you now dig through different studies, talk to different stakeholders, to different institutes, to different think tanks, they always will give you a different answer. And if you talk to them again, a couple months later, a year later, they maybe change the perception. We all saw, at least in Europe, the hydrogen bubble. Everybody wanted hydrogen. Then they realized, ooh, not available. Okay, what else? Let's go electric. Also not that easy. Let's just stick with natural gas. But it's not helping. So, and this was our starting point where we thought, okay, we need to do something here. We need to develop a solution which is as flexible as possible to support you and your end customers on the trip towards a carbon neutral future. And if you take a look at different agencies and even Honeywell itself, everybody is heavily committed now. Yes, some areas turned a bit into a different direction for now, but the overall trend towards a more sustainable future will not change. Honeywell is heavily committed. We are spending about 60% of our R&D resources towards a more sustainable future. And all agencies out there are heavily looking into this. If you get a bit more specific, what does it mean for our industry of industrial process heat? If you look at a rough assumption, this industries for heating and cooling is consuming about 45% of the global energy. And as already mentioned, is responsible for about 30% of the CO2 emissions. If you get now a bit more specific for Honeywell Thermal Solutions, we estimate, and this is was a pretty difficult thing to do, that we have about 1.2 million burners in the field up and running at this point of time. 99.99999% of them are operating on natural gas. If you take a look at the US and Germany only, these countries are consuming 2,000 terawatt hours of energy per year for industrial process heat. And with this are emitting alone, these two countries, about 445 million tons of carbon equivalent each and every year. In the European area, we trade these emissions in emission trading schemes. If you put a number behind, we talk about costs of about $445 billion. So there's also an incentive for companies, at least in Europe, to do something about this. Here's a view how I think our market might evolve. And it's not easy to project something like this because it's changing on a daily basis in a rapid pace. So we come from the fossil fuel standard emission age. There was a bit of low emission. Think about areas like California, water stringent on NOx, even China, really hard NOx emissions. If we look through the next decade, we are projecting that fossil fuels and standard emissions will get less and less. It will be partially replaced by low emission solutions, low NOx burners, for example, low CO burners and all this for different applications. Portion in the renewable fuels will become available. Hydrogen would be an option, DME, ammonia, biogases, and they will be taking part in this industrial process heat market. And for sure, electric heating will grow significantly in industrial process heat. So we're going away from a rather uniform market into a highly fractured market. If you look at the US, you already might see for certain areas, you have significant amount of renewable electricity coming into play. This will change the industrial heating market step by step. Same goes globally. If you ship your equipment or your components globally, this will affect your business model down the road because these things will happen on a global scale. And with this, we said, okay, we need to be flexible. We need to develop a technology where we can integrate, ideally, fossil fuels, mainly natural gas, renewable fuels, could be biogas, could be, for example, hydrogen, as well as electric. And we did this in a way where we say, okay, we're not going full electric just yet. We're trying to electrify important points in operation, holding temperatures. As you reach a recirculation point, we say, okay, now I'm having a steady state process. And with this, we only can decarbonize partially. We estimate up to 30%, could be higher, could be lower, depending on the process and the exact application conditions. But it's a stepping stone towards the future. And it's not only driven by sustainability itself. There's more to it. If if you combine different heating technologies into one system, you can improve your temperature control. You can reduce temperature overshoots. You can significantly increase turndown while not affecting your CO emissions as well as NOx emissions. I'm going to show you one of the examples later on. For sure, lower CO2 emissions already mentioned, especially later on by combining hydrogen and renewable electricity. The combination with the significantly increased turndown will give you a really good environmental compliance. Think about California. 20 ppm, we have burner solutions which are able to guarantee this, but at a limited turndown range. With this, now we can increase the turndown significantly without sacrificing emissions. And if your electricity comes from a renewable source, it can be cheaper. And I'm going to show you an example at the moment for Europe, but I also have some for the US, where this can be used to reduce your operational costs by tapping into the stock market on electricity and gas prices and allowing the switching of the system to the most cost-efficient heating method. So where are we looking currently? We are looking for verticals and applications where we see a trend to become carbon neutral quicker than others. We see a big move in the automotive space. With the more switch coming to electric vehicles, automotive companies try to produce as carbon neutral as possible. We already see complete all-electric automotive plants in Europe. Same goes for building materials. If you look into the ESG roadmaps, on the sustainability roadmaps of the big building materials companies, Knauf comes to mind with Europe Gypsum. They are heavily committed to becoming carbon neutral in the next decades, 2 decades typically. And they are investing now. They're already starting up the first full electric plants in Europe. And I'm going to show you one of these projects we did together with one of the companies in this building material space later throughout the presentation. HVAC, think about air supply units. It's a wonderful example for a hybrid solution, combining electric and combustion into one system to make the burner a better piece in there. Asphalt, glass, metal, for sure also pushing heavy, not there yet, but you see trends happening there. Food and bev. If you go through a European supermarket, you already see first beverages, first packaged food, having labels on there, I am carbon neutral. So now they are marketing heavily towards the end user and end consumer, and they are leveraging this to try to sell the product at a premium. So we see a movement there happening. So where we're currently looking is in the low mid-temp ranges. You see from also the application price. We limited capacity, so it's going to be small scale and application-wise drying. This was our starting point, by the way. We are now expanding significantly. So now we are tapping into megawatt electric systems already. But there's where we came from, and there's where we're going to be at least the first into market. So what is a hybrid system? It's on paper, what a simple thing. Imagine every process which needs heat. And now we come with all our legacy brands we own from a burner company, a combustion company. We know our burners in depth. We know our burner management systems in depth. Could be a 7800, could be a Slate, could be a BCU of Chromschutter. On the electric heating side and the power electronic sides, we decided to select a handful of partners. So we have partners globally, we have some in the US, we have some in Europe to support us on this special domain knowledge. And then came, to be honest, the most difficult task. So mechanically, to build up a system which consists of 2 different heating sources was not too complex. This was done rather quick. The most complex part is to develop a control unit to seamlessly switch and also safety-wise switch between the different energy sources on the fly in the process without affecting the process. And I'm going to show you one example later on we did together with a printing company. But let's start at first out with temperature control and our first ever hybrid test that we built. It consists of an NP burner as a duct heater with electric heating elements. And what we're able to show here is that the system is able to operate on a pure combustion. You can see some thermographic images taken while operating it. You even can recognize the flame in the center. You see the all-electric operation and a hybrid operation. So we took this picture at about 50-50 composition between electric heating and combustion. And with this, we can flexibly switch between fossil, what could be renewable fuels, depending on availability and price, as well as full electric solutions, and back, or mix them. And we were able to show in this prototype system that the temperature control, the temperature distribution, gets even better versus a simple combustion system. We now use also the electric portions to profile the air to smoothen out the temperature profile in a short range after the burner. On top, we saw this electricity prices getting volatile in general price in general. So if you take a look at the natural gas price index globally, for oil, we know it quite a while now, we see a volatility. And using this flexible heating system, you can hedge against this partially. I already mentioned the NP. NP is a burner which is able to take hydrogen as a fuel. So we look towards the future and we project that hydrogen will become viable more and more. So there is a significant reduction coming. And with this, you can already hedge the bet on, okay, if I invest now into a flexible system, which is able to run on natural gas, hydrogen, and partially electric, it's independent of what comes in the future. I'm at least partially safe. And this is what we're trying to advocate. Let's go a bit more into the solution details. We are going to show you today 3, at least, prototypes and projects we are at a really, really good stage. We pushed out in the market, they're up and running already. And they're going to show you some ideas we're currently negotiating. And I give you a sneak peek in the next upcoming project we just won. We categorize our hybrid solution into 3 different buckets. Option number 1, we call the turn-on extender. And this is especially aimed at markets with rather stringent NOx or in general emission limits. Again, think West, California comes to mind here. And this was a co-development between us and a customer out of the printing industry. They struggled in California with the 20 ppm limit if it came to significant turn on. This system is consisting of a Linux burner, really good no NOx burner, able to guarantee the 20 ppm limit there, but in a limited turn on range, and they needed more. So you could now think about, let's stage burners, we can do multiple, might be a viable option, but it's also not that simple. The controls get rather complex. So we came up with this idea where we combine a Linux burner with a really small electric heater bank, top and bottom of the burner. And the electric heaters will only provide about 20% of the capacity of the burner itself. And I'm going to show you real pictures of the system from our Muncie lab. So if somebody wants to see it, please reach out to AJ or directly to me. We can organize a visit at our facility that you can take a real life look at it in operation. Category 2, we call the flex heater. I already showed you this. Here the idea, you can flexibly switch between energy sources. And this system can take multiple shapes and forms. I'm going to show you some ideas throughout the presentation, how you can execute on it on a real life base. This is one example I show you here, but there's more. Option number 3, with the really short and really good name, but it's not going away anymore, sadly, electric preheated combustion air. This combines another mixing burner, in this case, what I'm going to show you today as a project, our Kinetizer LE, with an electric flow heater. Here we use the electric flow heater to optimize the combustion by providing the burner with preheated combustion air depending on different demand signals as well as temperature points throughout the process. So we are augmenting the burner with a small electric heater to make the burner better. So let's dive in. This is our Muncie prototype. Here's the photos in our Muncie lab. We try to mimic the customer process as good as possible. So we built ourselves a small electric preheating duct you see on the bottom. Now it's probably a good point to pull up my laser pointer. Here, where we control the preheat temperature. Then it goes into the main ducting, and up here, blower, Linux, electric heater bank 1. At the time we took the photo from the back, you see here would have been electric heater bank 2. It was disassembled at the time we took the photo for some maintenance and testing. If you now look into an operation, and this was one of the first runs we ever did back in November. Up here, temperature is a function of time. Down here, capacity. Be aware, kilowatt. I know, different from what you're used to, but we needed to set it on a unit where we can compare electric and combustion in a good way, so we're with kilowatts. The complete system is operated by a slate. So we developed a complete new state machine approach for slate, which is driving the whole prototype. So the slate is the burner controller and the brain combined in one. So up here you see, at the time, we simulate a cold start, we enable electric heaters that can kick in right away, and then there's a slight delay, safety check, pre-purge, burner goes into operation, temperature rises, we are stabilizing. The black line is our demand signal coming from a temperature controller. It's just a simple 4 to 20 milliamp signal. And here, for the customer, we did this operation, we just simulated, okay, system is up and running, we now go into recirculation mode. Demand is dropping, preheat temperature here in a dashed red line is increasing. The system automatically recognizes, oh, I don't need this much heat anymore, switches to an all-electric state, is maintaining all-electric. You see here, down here, the capacity of the burner drops to 0, and down here, the blue and teal line is the capacity of the heaters, fluctuating slightly to maintain the heat load. As a second part of the simulation, we just said, okay, let's assume there is a different product running through. We have a higher heat demand now. So preheat temperature drops because the product absorbs more heat. We see an increase. The burner is enabled again. We are stabilizing after a short period of time. And now we are in a hybrid operation where burner as well as heaters are enabled in conjunction. As I taught first runs, with the newest ones, but I don't have a nice graphic as this, we were able to smoothen out these transition pieces almost perfectly now. And with this, we estimate we are not only providing a significant turn-on with stable CO and NOx emissions, as well as up to 20% CO2 savings if the electricity is carbon neutral. And we are running a lot on reserve. It depends now on the process. That's why up to. Application number 2, our preheated combustion air solution is now in operation at an automotive company, factory in Germany. Legally, we cannot share the name, but I can give you a hint. Think about electric cars coming from the US. You probably know who it is. We are running there a kinetizer LE together with electric flow heater, again, powered by slate, to optimize emissions for the brain drying operation. So they had an issue that they needed way more turn down than they could get out of a conventional combustion system, in conjunction with extremely low CO and NOx emissions. With this, we developed this prototype. And here is how, the prototype operates. Again, kilowatt, because comparable electric and burner. Output as a function of the demand coming from the system. For a small area down here, the system is able to operate all electrically. to just keep the heat exchanger of the paint drying oven warm. So you don't need to shut it off. You just can run on a small scale electric to just keep it warm. We don't need to heat up anymore. This state you could probably run while there's a production stop. There's a change somewhere. There is an issue, but we still need to don't shut it off. We can keep it warm without any emissions at this time. After this, we can switch into a hybrid mode where the burner is enabled, running. We give it a bit of preheat to optimize the combustion and to lower CO emissions. And after the point where we know, and I said already, we know our burners really well, at the point we know can guarantee the CO emission limits, we go into a full combustion mode up to the maximum capacity. I've been to the site myself, and you really see the system switching between different states, depending on the occupation of the paint booth and the process where you are down the road. So let's talk now a bit more solutions. And now we have to go to a bit of hand sketching, because typically if we sit together with a customer, we at first look, okay, what's the application? And we just draw some hand sketches together with them, say, could this work for you? And these are some projects we currently either already are executing or we are negotiating. So together with multiple automotive companies in Europe, we are working on a hybrid air supply unit. We have a burner and we have a lot of space to install some electric heaters in there. And especially if you think about rather warm regions in terms of climate, Southern Europe throughout the summer, a lot of sun, you could run this air supply unit all electric without any problems for zero operational cost. And in the winter, if it gets too cold on the outside, you still have the burner as a backup, and with this, you can optimize your OPEX significantly. Another project we are currently negotiating is a hybrid fluid bed dryer. The customer wanted freedom to switch between different energy sources, depending again on price and availability. And here we had a bit of challenges to overcome because the process required a rather continuous and stable process airflow. And if you would switch on and off the burner, you would have an external air supply, you would then have to readjust the fan, and this could affect the process. So here we designed a system where we have a side-mounted blower. So we take the combustion air out of the process airstream and feed it to a burner. In this case, it's an NPN box. And the burner is surrounded by electric flow heaters, similar to what I showed you before. And with this, the system can either run on all electric. We can take partially the air out of the stream and feed it to the burner, hybrid, or we can turn off the heaters to just add like in the end, flow straightener, and the burner is only running. So the system gives you full flexibility, it's hydrogen ready, you can pick whatever you want. Another project, again, this time a nozzle mixing burner. It's an OPLE in this case. Here mounted in the center, will be surrounded by 4 electric flow heaters. And again, the system can flexibly switch between combustion and or electric operation. Only down part here, the space requirements you have, they increase a bit. But if you have it, the space, and you have access to cheap renewable electricity, it's a way to go to decarbonize your operation really quick. And last but not least, I already teased it a bit, our newest project, and here this is really already being worked on, but still, at the moment, I still would like to sketch. It's a hybrid gypsum mill. Will be operational summer next year. We're currently in the first stages of the project. And here, this is a combination of a ratio star burner from our portfolio, which will be supplemented by a significant amount of electric heating, in this case, 1.5 megawatt of electric heater bundles. So going to be 5 of this, about 2-foot long, 1,000 pound heavy electric heater bundles, which can run the whole process or preheat the air for the ratio star down the stream, which then will provide the final rise in temperature. The system will be operating at about 950-ish degrees Fahrenheit, so 650 degrees Celsius, so rather high. The ratio star in this case is designed to run also on hydrogen and with minor modifications also on a biogas. So this is one of the most flexible systems we ever executed so far, and we're just ramping it up. If you look a bit more into this cost and efficiency issue, and now I treat the numbers, I re-looked up the numbers for the US. This was quite surprising for me, but natural gas still really cheap. Again, I opted for megawatt hours. I know unconventional unit for you, but it makes it easier to compare thermal combustion with electric because it's in the end the same unit. It's rather common. So combustion in the US at the moment about $17 per megawatt hour. It's about $4 to $5 per million BTU, plus minus a bit. Hydrogen. These are estimates. Nobody knows so far what hydrogen might cost down the road. We estimate it's going to be at least a factor of 10 more expensive in this ballpark in the US. But if you have a more accurate number, please feel free to contact me. I would be happy if you have some more insights. And if you think about combustion, it's a really well-known and really good technology. But sadly, typically it's attributed to a significant CO2 emission. If you would calculate it, it's about 200 kilograms of CO2 you emit while you burn 1 megawatt hour of natural gas. A really big advantage is it has a really high local power density, and with this, a really good convective heat transfer. It's still difficult to increase efficiency in standard combustion systems. You need to invest into heat exchangers. With this, you get other down parts. The control gets more complex. You might need insulated airlines. Recuperative burners are also not a cheap thing to do. And okay, I know this point applies more towards Europe. We learned it the hard way. Energy supply can be volatile, especially at the moment for Europe. If you think about all electric solutions, the typical price for industry users tapping into electric grid, and this is the average, is about $116 per megawatt hour. It ranges significantly depending on the location in the US. So it can go from the lowest I ever found was about $40, $50 plus minus a bit, up to almost 150, 200. It really depends in which state and area, even within the state, in which area you look. It's also a technology which is around quite long. It's again, we can decarbonize, but you need renewable electricity. And we come to this just in a second. The big advantage of electric heating is if you can use the radiative part for indirect heating, the efficiency is increasing significantly versus a burner. And there are industries and applications they rely on this for decades. A lot of furnaces for the aerospace industry were always running on electric heating. So there's nothing new for them. But the expansion brings significant down parts with it. The CapEx for new transformers, substations, grid connections is not to underestimate, especially lead times. Currently, the biggest companies in these areas are giving lead times for new transformers in the areas about 7 to 10 years for megawatt transformer stations. And even if you're able to buy one and get it delivered, where do you put it? Footprint might become an issue, especially for traditional existing installation. There's no space. You can put it in a parking lot, but okay, not everybody will be happy about this. Power density is still a bit lower versus combustion. They're catching up significantly. If you think about scalability, if you look into your standard combustion system, If they need a bit more capacity, okay, sure, not a problem. Let's overfire the burner slightly. It was always possible. With electric, yes, there is a bit of security typically baked into it, but it's more difficult. So scalability is more complex than before. The overall project in general becomes also way more complex. You need to talk to different stakeholders. You need to look into different safety measures depending on the voltage you're using. It's not to underestimate what brings this. And also, as far as we still know, the investment for the combustion, for the heating system now is about 2 to 3 times higher in a furnace on high temp. There we have really concrete data. It depends on the application. It can range a bit. If you would run the electric heating system with renewables, the price can drop to zero. In California last year, there were about 2,000 hours throughout the year with zero or negative prices for electricity. Same only applies throughout Europe. It ranges between about 200 hours a year up to about 1,000 hours a year, depending on the country you're looking into this. But people and more companies are tapping into even your private household. You can do this now. You can buy electricity like on a stock market and trying to benefit from this days where we produce a lot of renewables. And now the hybrid system. If you combine combustion and electric, and here's a mix of 70% combustion, 30% electric as a guidance, you already see grid, no way. It's way more expensive and it's even dirtier than using natural gas because the overall grid in the US is still relying heavily on electricity from coal. So with this, the CO2 footprint on average, again, depends on region, sub-region, could be higher. If you look into running it with renewables, not only are you able to save money on your operation, you also emit about 30% less CO2 which is a second currency we now trade in nowadays. And as I already mentioned, depending on the design of the system, we are hydrogen ready from the first day on. So you're not blocking this avenue by going on electric. I already showed you that depending on the application state, we can switch between different points of combustion, electric, both. And with this, we're able to increase efficiency. We don't need excess air anymore, like we did before. And we are also working on projects where we can implement this electric heating to improve temperature homogeneity in different furnaces. We already know for air heating it works, but we're also looking into higher temp applications as we speak. Later on, if the hydrogen becomes available, currently not viable, would be the best case in terms of CO2 emissions, not there yet. But there are also some down parts of hybrid, for sure. Yes, it is more expensive than a standard combustion solution. And I'm going to show you a calculation in a couple of slides. And yes, we need a bit more footprint in terms of controls. So your control system is not only a simple burner control now, like a 7800 or a slate. The panel we need is slightly larger. We need to put the power electronics somewhere, but typically it's acceptable. And since we limit the amount of electric heating in the system, we tailor it. We can limit the amount of capex and therefore also the size of the system. So in summary, we can save about 30% with almost identical cost per megawatt hour. And now to the important, what's the payback? And here I did the total cost of ownership estimate. We're currently working on a project and I just use this as a guidance. It will be a dryer for roof tiles. Capacity about 1.5 million BTU and 50% of it we can supplement electrically. And for the sake of this calculation, we assume we have our own solar cell system now up and running, producing a lot that we can run 50% throughout the year electrically. And this is a customer, that's why I took the example. It's working. And yes, currently the domestic payback in the US is not there yet. But I already told you, sustainability is here to stay. It might move a bit slower currently, and it will take a bit longer, but ESA payback is far from ideal. Nowhere to hide it. It's about 10, 11 years-ish currently. But who knows what the future will bring? Maybe we can drive it down. And if you look into the European area, there you see already, and this is just the same system, I just changed out the cost for the gas and the electricity in Europe. And you see there, we already achieve a payback in the area of 2 up to 3 years, depending on the bit of design the system. And there it becomes really viable. Shorter than 2 would be perfect, but we already see that a lot of companies are increasing their CO2, their payback goals for sustainability initiatives up to 10 years. Because if you want to become sustainable, it will cost a bit more money, for sure. But as I thought, we already have it. And this calculation doesn't factor any incentive and subsidizes into it. So these are European ones. So this looks a bit more, this gives you a bit more guidance if you export machinery towards Europe, where to look for. In the US, currently, there are no incentives up and running, but let's see what the future brings us. There might be something coming in the future, but here you have some ideas where to look for in Europe. We have the European emission trading system, and if you can, the end user can apply there, and the trading scheme works the following. You can show avoided carbon, so how many CO2 tons I save throughout the lifetime, and you can back this as an incentive, which makes it significantly more attractive. There's an innovation fund we can tap into, and there are also federal options like this is a German one, the EEW, as well as the NDS Europe Fund. And down the road, there might be similar options available in the US to support this journey, and then we might be able to significantly improve payback. One of the last slides for me. Why Honeywell? It's always important to remember this. Our name is not Honeywell Combustion Solutions. Our name is Honeywell Thermal Solutions. And given our combined legacy in the thermal business, we have more than 100 years of experience in it. We shipped a significant amount of complete systems. Combustion mainly, but now we're going towards the future to become a complete thermal provider. We have more than 60 global field staff globally running everywhere to support this commissioning, to support you. More than 3,500 customers in more than 100 countries. And with this, I want to thank you for your attention. If you have any questions, I'm happy to answer them.
Tobias, thank you so much. It was very informative. And I, again, as Tobias mentioned, we can open this up now for any kind of questions that you guys may have for those of you that are attending live. And while we wait for them to either type the answers or you can actually unmute yourself and ask directly, I will let those know that are listening to the recording of this on the link to the training center, there will be a contact us, or we'll have a way for you to reach out to us after the fact if you have a question for myself or for Tobias. Tobias, I do not see any of the attendees have any questions for us right now. So I think you covered everything thoroughly. So I applaud you for that, and I do appreciate your time. So with that, we will end the webinar. I do thank you for attending and listening. If you have, again, any questions or you're interested in learning more about Honeywell Thermal Solutions, please feel free to reach out to myself. I'm, again, AJ Piskor. You can reach me at ajp@lessman.com, or you can contact us through the website at the phone number there, and they can get you in touch with me and with us. So again, Tobias, thank you so much for your time. Attendees, thank you for attending, and everybody have a wonderful and safe day.
Thank you. Bye.
All right. Thank you, Tobias.